My name is Mariusz Saba, and I will provide an overview of the secret lifecycle management for microservices in Container Cloud, also known as Trusted Service Identity. So what is the problem? Today, in OpenShift Kubernetes, in order to exchange or retrieve any data, microservices store authentication information in secrets. Once the secrets are stored, they are also available to Kubernetes admins and everyone who's sharing the namespace. But the administrators might be third-party employees, might not be certified to access this data, they could lack security clearance or legal requirements like specific citizenship. There is also an increasing need for accurate audit trail to track who accessed what and when. Let's take a quick look at the hypothetical scenario in today's practice. An application composed of several microservices is deployed in Kubernetes cluster. These services need to access databases. The operator generates certificates or keys and stores them in Vault, then creates secrets that application can use to access the Vault or the databases directly. But what if the admin or operator is not certified, careless, or malicious? If applications are deployed in multiple regions, locations, the secret management problem is even more exponential. Secret management techniques in use today make secrets accessible to cluster administrators. Let's take a closer look. Container uses the secret to access the database. Problem is that typically the same secret for accessing Vault would be given to all the instances of the application, and that makes this audit much harder. The secret is available to everyone who has access to this namespace, including the administrators. Even if we move all the secrets for accessing the database into Vault, we still need to authenticate the application somehow, so it's able to read from Vault. The admin can use this secret to read the database from Vault directly. In addition, humans create and inject the secrets to Vault and to Kubernetes. Finally, the secrets are static and have no limited lifetime. The IBM research team has been working closely with Data Platform Group to address this problem. The solution is called Trusted Service Identity. As a result, Kubernetes admins cannot view the secrets because there are no secrets stored in the cluster. Secrets are stored in a secure vault, which is significantly reducing the attack vector. Trusted Service Identity, also known as TSI, retains full, detailed audit trail, so we have a detailed record of who, meaning what process, got what and when. Permissions are enforced based on the workload identity. Policies and permissions can be dynamically modified, keys revoked without changing anything in the deployed application. Access to data might be dynamically terminated, secrets might expire as needed or rotated. Our solution allows for very fine-grained access control. So how is it done? First, container gets assigned a short-lived measured identity in form of the JWT token, a digital biometric signed with root of trust. Then we have policies that define what identities can get access to what secrets. The secret store, Vault, validates the token signed by intermediate authority. Lastly, secrets are released to the workload applications based on their identities and the policies. Here's the architecture overview. In the pictured example, we want to protect access to the sensitive data in IBM Cloud. We also have a kube cluster extended with TSI, where each node gets intermediate CA signed by root CA during the secure bootstrapping of the cluster. Each node also has a JWT signing service that contains signing authority. Today this is a software, but we are working on the hardware TPM version as well. Root CA is securely stored in Vault. Vault is extended with our authentication plugin. Before we begin, Chief Information Security Officer or some other secure process deploys in Vault secret keys for accessing the cloud and database. Then creates policies that define what are the characteristics of the application that can get access to these secrets. Now we can deploy an application in this cluster. This application wants to access the cloud and data. If the application is annotated to use TSI, the modified admission controller would start the sidecar. This sidecar collects the measurements about the application in form of a claims, then sends the claims securely to the signing service. Signing service signs the claims using the intermediate CA and returns the JWT token back to the sidecar. Sidecar requests the annotated secrets from the vault, passing the JWT token along with the request. Our authentication plugin in Vault intercepts the request call, validates the signature and the expiration date on the JWT token. And if everything is okay, it uses the claims provided in the request against the policies. If the measurements match, the secret is released back to the application. Sidecar mounts the secret to the running container the same way as the regular Kubernetes secrets are done. Now the application can safely request data from Cloudend. So the secret has been delivered to the container runtime memory without being stored anywhere in Kubernetes, but from the point of view of the application, there was no additional changes needed. Here's the example of the JWT token. It is composed of three parts: the header, payload, containing the actual claims, and signature for validation. These claims included here represent the measured identity of the application. They include the cluster region, for example Germany, cluster name, individual machine ID, which is the worker node, unique pod ID, a list of images making up the pod, including the image signature, so the image can be validated and guarantee that the application is running the code that you want to be running, and nothing was tampered with. There is also an expiration timestamp, typically set to 30 seconds, so these tokens are quite ephemeral and short-lived, protecting the security from leaking. Here's the sample policy. It is called TI demo all, as it contains a path to the key using all the main attributes from the claims: cluster region, cluster name, namespace, and encoded image name. This policy grants read access. The second policy defines a path using only two measurements: cluster region and image. Simply put, it allows a read access as long as the container is running from the specific region and it was instantiated from a specific image. Now let's try to create sample keys that are using these policies. In this example, we inject to Vault a secret that is using a policy demo all, and it has the specific path pattern. For example, it is running in region Germany, cluster name EU cluster, namespace trusted identity, encoded SHA image is this long line. And the value of the secret is very secret value. The second example shows the injection that is only using region and the image SHA. Then, in order to retrieve the secret from the container, we have to create an annotation that sets the injection to true and provides a list of secrets to be injected. The first secret name is MySecret1. It's using the Vault path specific to the demo all policy pattern, and we want the secret to be mounted locally in the container to the location MySecret, MyUbuntu, MySecret1. So as long as the container attributes match the path provided above, the secret will be injected to the specified location. Same of course for the second secret. So here's the sample list of use cases that we can address using this trusted identity model. Data about Europeans cannot be accessed outside of the European boundaries. Policy could be something like release the read access to CloudEnd only if the application is running from a trusted image validated by Vulnerability Advisor and it's running from EU location, which by the way is the example of the GDPR. Selected image versions must be executed only in specific data centers, on specific accounts and clusters. Provide a short-lived access to data with the quick expiration date, or dynamically and continuously rolling secrets. Common deployment code across multiple clusters with restricted data based on the location, or we can provide different data for different environments. For example, deployment and staging would obtain different data than production. We also have a fine controlled dynamic release of secrets or configurations at the specific time during runtime. So let's reiterate the business values of TSI. Increase security by eliminating Kubernetes admins access to secrets and data. There is no secrets stored in the cluster, which is significantly reducing the attack vector. Improved operational overhead and provides detailed audit trail, provides a best practice patterns for secret management and distribution. It addresses several security compliance requirements for FedRAMP and HITRUST. In compliance aspects, provides consistent and standardized way for enabling compliance controls. It's reusable and easily deployable tooling. Automated, eliminating human error, thus agile and scalable, significantly reducing operator work due to the compliance changes. It streamlines the DevOps process for managing secrets and provides the secure cluster and node bootstrapping process. This concludes the demo. Thank you.